screens organized. So up next we have Chetan Joshi with PTV. He'll be presenting on calibration of Meso and simplified car following models. Chetan's a principal engineer with the PTV Group. He is involved in providing travel demand modeling and simulation services to clients in North America and select projects worldwide. He also works on prototyping and testing of features in both vZoom and vSim. So take it away, Chetan.
Yeah, thanks, Randy. Can you hear me?
Yep, loud and clear.
All right, great. So we've seen some cool project applications earlier, and this one probably will be quicker, but we thought we always asked about questions related to methodical calibration of car following parameters and such. So thought we'd do something in that direction and share some results. So we talk about simplified car following models in this presentation. Here, the background for car following. We have car following model generally described as an approach to model traffic behavior. In the context of traffic simulation, it's used to capture the interaction between a driver and car with the surrounding traffic. And then the motion of vehicle is generally modeled as sort of control systems approach, where there's feedback between the lead vehicle and the following vehicle and constant correction for some sort of speed differential. In traffic stream flows, there are typically two types of traffic stream flow models. One is a single regime model. So in this kind of model, same model is used for congested and uncongested flow regimes. And this is more typical of earlier generations of models. Some of the more known models for single regime case are Green-Shields model, Greenberg model, modeled by Drew and Eddy, and so forth. Multi-regime models are different in that there is a certain critical capacity or saturation rate, and based on certain internal rules, it's typically modeling the flow in two regimes. One is the free regime, where there is no congestion, so it's essentially the free flow regime. And then there is a congested regime where a different following model is applied for the following regime. It was developed to overcome some limitations of the single regime models. Examples of the multi-regime models include the Wiedemann 99 and 74 models used in vSim, Gibbs model, which you might see in IMSUN and such, and then Pipes model, which is more generally kind of the linear or simplified model, which you might see in Core Sim, Free Sim, and so forth. So in vSim SBA or vSim simulation-based dynamic assignment, we have implemented a simplified car following model or linear model, which is kind of like a Pipes model like car following model. Over here, one of our objectives then was to calibrate the simplified car following model methodically and with data sources that are more generally available. For example, ATR like loop detector dumps and so forth, and use that macroscopic data to derive some of microscopic parameters required for the car following or simplified car following model. And then see if the procedure can be standardized that's also kind of transferable, because sometimes data is not that cleanly available. Loop detectors can be broken sometimes and not easily accessible and such. So Oregon, for example, has all of these different station locations, but we were not quite able to extract the detail, speed density. But it seemed like Peter got some luck with the portal data. So that would basically be the type of data that you would look for calibrating these car following models to get the speed density relationship and such. So the general methodology or background on this is that simplified linear car following model in vSim SBA is kind of based on Pipes like car following model form, which basically means that the fundamental diagrams would look like this. So it's a triangular fundamental diagram for flow density. And you can see that there's a branch over here, which is the lower branch of the model with speed flow, which is the congested regime, and the flat branch is the uncongested regime. So those are the two regimes of flow in this particular model. The mathematical form of this is essentially given like this, where headway has a linear relationship with a certain model parameter and the speed. So converting that with Q is equal to KU, the basic equation of flow, you get this kind of relationship. Over here, you basically have headway, density, Hj is the jam density, Q is the flow, U is the speed, and C over here is a certain driver sensitivity parameter. And this is what we try to calibrate or tune for calibrating this car following model, which yields that capacity or headway that gives you the simulated capacity in that dynamic assignment. Now, with this pipes model formulation, we have this property where the model basically has these kind of boundary conditions. So in the congested regime, your Q critical is like Q max. So if we just solve for these boundary conditions in the prior form, we can directly get that driver sensitivity parameter C as this C is equal to 1 divided by QC, which in this case is kind of converges with Q max, and then the jam density and free flow speed. So this converting this C into seconds yields for us the reaction time directly, which is an input into the car following parameter. So tau gives you just basically a multiplier into 3600, and that gives you the reaction time input at the network level. So this would be entered, let's say if you're doing this in VZOM, you'd enter this reaction time for a network level, and then you can further add a multiplier for specific links in the network if there are specific behaviors or calibrated behaviors observed over there. So then the model calibration essentially requires 3 items. One is the free speed, one is the jam density, and then the capacity. And these are readily available, generally speaking, from your loop detector dump. So these can be utilized then for calculating the reaction time, which goes into the car following model. So here we had to create this application example. So here on US 26 Sunset, we have a nice corridor with different features or bottlenecks that can be used to test this car following model and its parameters and such. We created a small network over here for the dynamic assignment. And then over here, we have a set of general freeway links in the corridor. And then there's that Vista Ridge Tunnel bottleneck. So you're going to capture 2 types of behavior here. One is the general following behavior on the usual urban freeway type links. And then what happens upstream of that Vista Ridge Tunnel, which might be perceived as a certain bottleneck with that other complex geometry that's further downstream of it. So I explored the state of Oregon ATR data, didn't have much luck in getting a detailed loop detector dump over there. And this was just on public domain, so maybe that data is available if we put in a request at ODOT. But then we also looked at some transferability or how that would perform. So then we had some loop detector dumps from I-4 Orlando, which is kind of an example of an urban freeway. And then the Holland Tunnel, which connects Lower Manhattan and Jersey City. And that would be kind of like that tunnel type of bottleneck. And the shape of that data looked like this. So on top, you can see the I-4 urban freeway shape, and then the Holland Tunnel, a little more sparse, but still somewhat useful for calibrating the model. Now here, based on the prior equation that we had listed, the urban freeway links got a reaction time of 1.47 seconds, and then tunnel links came to 2.57 seconds. And we entered this into the VZoom SBA and looked at how the queuing could be simulated on the Sunset eastbound. There was also a parameter for look ahead distance here, which was essentially for lane orientation, where you can say that the major branches of traffic are going north and south, and the middle lane on Sunset ends up remaining free. So to orient drivers towards one lane or the other, it's possible to then also put lane changing look ahead distance, which I won't discuss that much in detail over here, but I just placed that where that line marking or lane marking on US 26 kind of restricts the lane changing and such. But that is a separate topic for lane changing behavior, so not discussing that over here much. So with basic parameters, which were essentially like the default, which is 1.2 second reaction time, simulated the traffic here, and you can see not a huge amount of congestion seen. Traffic flows fairly smoothly here, and you can see some ripples in that pink in the corner over there, but then not a huge amount of delay is seen in this network. And we will look at some travel time segments and come to that a little bit later in this presentation. But you can see it's kind of that bottleneck is represented, but it's not causing a huge problem because it's all on the default reaction time, which gives it plenty of capacity to pass through. So next, we plug in just the urban freeway parameters, which is the 1.47 reaction time, and simulate that. And over here, then you can immediately see in that corner, again, near the Vista Ridge Tunnel, that there are more shockwaves going back in the pink, and it travels further back as we look at it. Over here, you can see that shockwave is a lot more pronounced in this case. And you can see that visually traveling back with the updated car following parameters for that reaction time. So it gives you an idea of how the shockwave flows back just with the change of one parameter over here. And you can see that propagating all the way back into traffic. Gives you an idea of where the bottleneck starts and how those bottlenecks propagate backwards. Then in the third case, basically we added the Vista Ridge Tunnel bottleneck function in there along with the urban freeway. And now you can see that a lot of the flow then just gets metered going into that Vista Ridge bottleneck. And you can see that the pink congestion portion starts at a different point, where if you have driven that segment, you may have noticed that you drive through some congestion, and once you get near the tunnel, you kind of get into a metered stream, which gets you through into your merged sections relatively without that much stop and go. Depends on the day, but generally. But a lot of the bottleneck over here, you can see that the shockwave propagates a lot further back, and the impact of that shockwave can be seen stretching much further back. So this kind of gave reasonable visual confirmation that it's probably not that great to use just the default. So you want to use some level of local calibration, as Randy had mentioned earlier as well. And then we take a look at travel time segments and such, and how those compare with these different parameters. One thing to mention over here, there are some routing artifacts over here that occur on that section of Sunset, where some travelers choose to take a small alternative detour to get back onto their I-405 South section and such. So here, this would be the usual route that one would take in free traffic. But in the congested stream, then we saw this with both the updated just urban freeway as well as the urban freeway plus tunnel bottleneck parameters, that this other route starts getting captured. So this kind of gives you that little variation of routing that can occur. Of course, the proportionality is still largely on the primary route, but that other route becomes attractive when conditions are more saturated and in cases where vehicles are not able to merge into that correct lane. So they take a detour and get back on track over there. Now, to validate some of the travel time segments, again, I checked the information on 511 trip check segments. Couldn't quite extract data from it, so probably just something that I don't know how to do with the 511 website. Need better understanding of it. But then we have always the Google routing. And nowadays you can give a departure time setting in Google and get sort of an expected range of travel times that you might obtain if you depart at a certain timestamp. So we were looking at this evening peak 5:45 p.m. departure, let's say, and then comparing that travel time segment with what we got in the Visum SBA with default parameters, with a parameter, and then 2 parameters with the tunnel as well. We looked at 3 segments here, one going straight into Market Street, one going north, and one going south, and this is the general range of travel time obtained. So how does this compare with what we got through the model? This is the kind of result here. So the Market Street, you can see with default, basically it just gives you a free flow travel time on the congested segment. So not much is captured with the default parameters if the simulation is done as is. With adding the urban freeway, now you can see a little bit more congestion and the travel time comes at least within the range. And then with the additional tunnel bottleneck modeled, travel time is further congested. And this general trend can be seen on all of the 3 segments that we look at over here. So definitely over here, what our conclusion came from that is that it is better to evaluate and consider car following parameters instead of using simply defaults where there is some data available that will give you more realistic representation of congestion and to be able to model bottlenecks a little more accurately in terms of where they originate instead of tweaking individual intersection capacities and such. And functional and available loop detector data, ATR data, can provide quite useful information for model calibration for these driving behavior parameters. On the ability to transfer coefficients of parameters, this was just one case, and kind of because we had travel time more in ranges, it was hard to conclude anything from that observation. So some more use cases and examples will need to be evaluated before we can say anything definitive about the transferability of those parameters. And that is it for me.
Awesome. Well, thank you, Chetan. Let's see. Any last minute questions for Chetan? Not seeing anything in the chat here. Or any other questions for any of our other presenters? Okay. Well, thanks again, Chetan, and thanks to
Randy, there was a question in the chat saying, how do you think the grade impacted the results?
Oh, I see.
Yeah, that's a good question. So here, in this case, we have a simplified car following model. So we don't take into consideration that aspect of vehicle dynamics. But I know what you're talking about when we are looking at sunset, that there is a grade over there, and that for sure will have some impact on the braking behavior and such.
Excellent. The other thing, Chetan, did you play around at all with truck percentages and how that might influence results?
Yes, that's right. And I did add in over here the fleet, basically what we used was actually a network that we got from Peter, and he had classified heavy and medium trucks in there. So they had those in PCEs in there, but then I reconverted those and used the Oregon State guide for these truck types and such, and assumed a truck type over there. Of course, it's not possible to get that classified data for the truck. So car following specifically didn't necessarily apply to one class or the other, but I did enter the truck types in there.
Okay.
And that seems to have made some difference in that queuing based on like when I did it without or with.
Okay, great. Then another comment came in from Mahmood. I think it is helpful if the calibration process is documented in Zoom examples so that everyone can take the same approach. I don't know.
Yeah, sure. That's a helpful link, and I will convey that to our product management.
Excellent. Well, we're a little bit ahead of time, so we can give you a few minutes before lunch here. On behalf of Oregon